All right, so what do we have here? Our first section is a review of functions. So hopefully you largely remember how to deal with functions, but we're going to go back. Most of calculus currently is taught from a functional perspective. So whenever you can write things as functions, we generally do, right? There's going to be times when you have to deal with things in equation form or some other form. That's why we have different ways of representing functions, so that you have a little bit of flexibility to use different types of tools. But usually we're going to be dealing with function notation, which we'll get to in just a minute. And usually we're going to be dealing with functions. As you progress through the calculus, you get more and more into things that are non-functions. So you have to bring other tools into play. But whenever we can, we're going to try to deal with things in a functional form. And in Calc 1, a lot of what we deal with is traditional functions, okay? So we have a few different ways of representing functions, and it depends on how your data is collected. It depends on what you're trying to do. It depends on the problem that you're studying, how you want to do this. So the first thing that we can do is use a table. So this often occurs if you have a finite number of data points that you collected or someone collected in some way. So this could be, say, population data. If once a year you go through and you mark the population of, say, a city, then what you would have is you would not have a continuous function because you wouldn't have information about the population at every single instant in time. You would just have it, say, at the beginning of the year, and then you would see how it moves from year to year. Now, for populations, that's probably okay. For other things, that wouldn't be the appropriate way to approach it. Okay, so you can see what we have here. One way of representing functions is with a table. So we have a table over here. We've got a column of x values, and we've got a column of associated y values. So if you look at any row, that gives us a point on our function. So this would represent the point 0, 0. This would represent the point 1, comma, point 5. This would be 2, 1. 4, 5, 5, 6, and so on. So then we can see over here, these points are being graphed. So those points in our table are being represented visually by points on the graph, right? And so this gives your brain two different ways of interpreting the information, right? You can imagine if you had a list like this of 100 points on that table, it's pretty hard for your brain to sit down and identify that information in a way that is usable, because our brains just sort of get overloaded when we just see a big string of text or digits or characters. But once we see it in a graphical form, your brain can start to pick up on patterns a lot quicker and a lot easier. So a lot of times being able to graph something, very helpful. By the way, the site that I'm using is called Desmos, DESMOS.com. It's a totally free website. They call it a graphing calculator. It's not as functional as, say, a TI-84. But if you need to get in there and make some really good looking graphs, this is probably the tool that you want to be using. So we've got this way of representing things. That's one way that we will sometimes deal with data, depending on, like I say, depending on how your data was collected. All right. A lot of times we'll be dealing with functions in a different form, which is either in our function notation. So remember, here's our functional form. Oops, what just happened? So here we've got things in a function form, right? So f of x equals x cubed. So this letter out front is the name of our function. If you're doing a problem that has more than one function, then you just give them different names. You could have a function that's f, you could have a function that's g and h. If you're doing a problem where the letters that you should use are obvious, then go ahead and do that. If you're doing a business problem and there's cost, revenue, and profit, then guess what? You should probably name the functions C, R, and P for cost, revenue, and profit. This keeps you from accidentally mixing up the functions, right? If you just always call them F, G, and H, then you might forget halfway through the problem which one is revenue, and then you accidentally grab the wrong function. But if you call them C for cost, then you're not going to accidentally grab the revenue function when you mean to grab the cost function, okay? And all you do here with function notation is you take an input, you put, whatever number you're putting in, you just substitute it in for x. So we can see if we put 0 in for x here, we end up with an output of 0. So the input is 0, the output is 0. That gives us the point 0, 0. And we can see that our function goes right through the point 0, 0. How about if we go to the point, if we put 1 in there? Well, 1 cubed is 1, so that would give us the 0.11, and sure enough, our function goes through the 0.11 right over here. Now, in this case, we've actually graphed an infinite number of points. In the last graph, we only had a finite number of points. Here we can graph an infinite number of points, and there's so many points here, and they are so packed together that we get what's called a continuous graph. It looks like it's actually just one object, this curve, but it's really made up of an infinite number of points on our graph. Okay, so that's how we're going to deal with functions. The majority of the time is going to be in this function notation form, and that's how we're going to deal with it. Occasionally, we will deal with things in equation form. For certain sections, it's easier to deal with things in equation form than it is to deal with them in function form. So that's preferable sometimes, and you can even see we can do the same exact thing. I mean, you can see how these two things, the equation y equals x cubed and f of x equals x cubed, are essentially the same thing. Right? We're just one is in equation form, one is in function form. If you're going to have to do a lot of fancy algebra on something, sometimes it's preferable and sometimes necessary to put it in equation form in order to get things solved how you want it. Okay, so those are two ways that we can deal with functions as well. Equation form, function form. Now, one thing that comes up in this section, and these are two great examples of, are even functions and odd functions. So you'll want to remember how this works, right? Remember back to your trigonometry. Even and odd functions come up a lot in the trigonometry. They can be helpful from time to time. So if you just remember, an even function has symmetry with respect to the y-axis. So if this screen was a piece of paper and I folded it right here along the y-axis and I folded it over on itself, one side of this curve is going to line up perfectly on the other side of the curve. That's what we call an even function. We say it has symmetry with respect to the y-axis. Okay. Then we have an odd function. This would be considered an odd function. It has a different type of symmetry. I can't really fold this. If this was a piece of paper, I couldn't really fold it in some way where the graph's going to line up on itself. But there are actually lots of types of symmetries in mathematics. We can have, in this case, this actually fits two different types of symmetries. We normally think of an odd function as having symmetry with respect to the origin. So that is, if I take a point on here and I basically shoot through the origin, right, go through the origin, and there's an opposite point, the equal distant on the other side. So if I take 1, 1, and then go through the origin the same distance away, I end up with -1, -1, right? So that's the kind of symmetry this has. It also has what we refer to as rotational symmetry. So you can imagine if you took this shape, kind of pinned it down right at the origin here, and then just sort of twisted the thing, halfway around it would line up on itself again. So that's called rotational symmetry. Although in this course we don't think about things in terms of rotational symmetry a whole lot. It's a little easier for most of what we want to do. You want to think about it in terms of symmetry with respect to the origin, but it's fine. Whichever way you think about it will work. Okay, so we've got those. And so here's an example of why we can't always write things in function notation. What if we have something that is not a function? Now, we can't just apply a lot of our algebra tools to anything that's not a function because a lot of our calculus tools that we're going to use are formatted in a way to be applied to functions. But sometimes, obviously, if you're dealing with something that's not a function, that's not possible. So here's an example, right? Think back to a circle. Here we have a circle of radius 3. This is not a function. So therefore, any calculus tools that I have that apply to functions aren't going to apply to this, right? But we will have certain things we can do that we can apply to this. Like implicit differentiation is one that we can apply to things that are not necessarily functions. Okay. How do we tell if something is a function or not? Well, there's a few different ways to do it. Remember, the definition of function is that each input, each x value that you put into your function has exactly one y output. Okay. And we can see that that fails here. One way to quickly determine if something is a function or not is you graph it. And Desmos can easily graph things that are in equation form that are not functions. As you see, you just put the equation right in here and it graphs it for you. So the vertical line test can quickly tell you if something is a function or not. Because as you can see right here, look at our line. We put a vertical line here and see how it's hitting our graph in 2 points at once. So what have we just found? We found one x value right here at x equals 1, and it has two separate y values, one up here and one down here. So we just found a place where this circle violates our definition of a function, which is that the input of x equals 1 should only have one y value output, but we found two. Therefore, this thing must not be a function. And in fact, we can scan this all over the place. This circle obviously fails to be a function at many, many points, in fact, an infinite number of points. Now, when you're trying to use the vertical line test, remember, you're not trying to pass the vertical line test. You're trying to find places where it fails. So sometimes I'll have someone and say, yeah, but look right here at x equals 3, there's only one output, y equals 0. Okay, that's fine at that point, but then over here we have an infinite number of points where it fails. And if you fail at one point, you're not a function, right? If you have you have to either remove those points, or there's all sorts of things we can do with functions. But you're looking for one point of failure, right? It's like a chain. If you have one point of failure in the chain, your chain isn't going to do its job. It's the same thing here. If we have one point of failure for a function, then we're not dealing with a function. All right, another thing we need to look at is domain and range. So basically for functions, what you want to remember, the domain are the values that you put into a function. The range is the values that come out of a function. Okay, so sometimes we restrict a domain intentionally. So for instance, we could take y equals x squared and say, okay, well, that's what that function looks like, but maybe we want to restrict this. So we can put a restriction on this. Okay, so we can put a restriction on that equation, and now we've restricted the domain to only be x values greater than 0. So we can artificially put a domain restriction on a function. Sometimes we do that like the regular y equals x squared. When we get to inverse functions, we know that function does not have an inverse. However, if we restrict the domain of this function, now it does have an inverse. And if you don't remember the rules about that, we'll talk about that in a couple of sections. But for now, just realize if you're on Desmos, it's very easy to go through and restrict the domain. Just kind of write the domain restriction in there the way that I did right there. Okay. So if we look at say we want to find the domain and range of a function. So from a graphical standpoint, this isn't too bad, right? If you're looking for the domain and you have a visual representation for it, we can look and say, well, it looks like the x values start at 2 and then they increase on forever. So it looks like for this function, the domain is 2 to infinity. Okay, including 2. Now, you might have to look in some of your functions. There are places where if you graph it, it will look like there's like it's continuous, but there's actually a tiny little hole in it. Desmos and these graphing utilities are not usually very good at emphasizing those holes where they exist. It just kind of goes over them. So remember, if you have a denominator in a rational function equal to 0, so where x is equal to 0, that value will not be in your domain. And it's the same inside of a square root. Any negative values we get inside of the square root, well, that's going to give us the square root of a negative number, which is a complex number. But most of the stuff that we do in this class is going to be involving real numbers, right? At least our functions are usually going to be involving real numbers. You might solve equations where you get complex numbers as a solution. But complex valued functions is this whole big complicated thing, right? If you become a math major engineer, you'll take complex analysis down the road, which is, you spend a whole semester dealing with stuff like that. It's a little beyond what we're doing in here. So for right now, when you see a function involving a square root, just remember, well, everything in here has to be greater than or equal to 0. So if you set x minus 2 greater than or equal to 0 and solve it, what do you get? You get x is greater than or equal to 2, which is exactly what we just said the domain was over here. Values that are 2 and bigger. Okay. Now, what about the range? Well, the range is all the values that you can get out of your function, right? So just look at your domains, plug in values and go, okay, I can kind of see what's going on here with the outputs. Also, we can just see it on the graph. What are the y values? Well, it looks like the smallest y value we get is 1. And then they go up from there. So it looks like our range would be 1 to infinity. Okay, so just remember, domain is your inputs, your range is your outputs, okay? So then we get to a set of functions that are, they look scary at first and they look kind of weird and bizarre, but they're actually not that difficult to deal with. So we have the absolute value of x, which looks like this V shape right here. It's actually just two lines put together. We have the line y equals x on this side of the graph. We have the line y equals negative x on this side of the graph, because if you think about it, that's exactly what the absolute value does. If you take the absolute value of a positive number, you just get that positive number back. Therefore, any number you put in as an x value just comes back as your y value. And what about on this side? Well, if you put a negative number into the absolute value function, you get the positive version of that number back. So essentially, you're multiplying it by -1. So those points are represented by y equals negative x, giving us this V shape. Right? Now, this is a little unusual of a function because it has this corner. We don't see a ton of functions that have sharp corners in them, but we will see them from time to time. And these sharp corners are going to be a little bit of an issue when it comes to calculus, right? We have things like, we haven't defined this yet, but when we get to differentiation, corners are going to be a little bit of a problem for us. So we can have difficulty there. This is one reason you're going to like polynomials. You may not have loved polynomials in your algebra class, but in calculus you're going to love them because they're smooth and continuous. They have really nice behavior. It makes the calculus on them a whole lot easier in general. So just be aware when you get a sharp corner, that's going to give us pause in calculus. We're going to have to take a little bit of extra care around that point. Okay, so if we take this, we realize we can take the absolute value function and we can write it as what's called a piecewise function. So your book talks about the piecewise functions, right? Notice this is actually the same function, but it's a different way of writing that function. So basically what you have in a piecewise function is you have numerous rules, right? When we have just a regular function notation, it's essentially giving you one rule to follow that says, take your input, apply this rule to it, here's your output. Well, with a piecewise function, what happens is you have numerous rules. So in some sense, the absolute value says, we have a rule when your x's are positive, that is you just return the same value back. But when you're putting in a negative number, the rule says to give back the opposite of that number, -1 times that number. So we have two different rules in this piecewise function. So how do you know when to follow each rule? Well, in your piecewise notation, there's going to be a description there that says when to use that rule. So for the absolute value function, it says when x is greater than 0, use the rule y equals x. When your x value is less than or equal to 0, use the rule y equals -x. And that's what you get over here. So when you see a piecewise function notation, don't get confused by it. All it's doing is it's listing a few different rules that you're supposed to use. And then off to the side, it tells you when to use each rule. Okay. All right, then we have what are called step functions, and the step functions come in all sorts of varieties. I'm going to give you the two most common step functions that you run across, but you can do all sorts of modifications to step functions depending on the thing that you're doing. This happens sometimes like in electronics where, things have to happen at exactly certain voltages, and so you'll have things jumping up to a higher voltage and lower voltage and stuff like that. But there's lots of ways that these come up. Two of the most popular step functions that you see the most are floor and ceiling. Basically, the floor function is where you round up. The floor function is where you round down. The ceiling function is where you round up. So they look kind of weird. They look like this. You can see why they're called step functions. It looks like you're walking up some steps here. So how does this come about? Well, the floor, remember, if we think about the floor, if you're told to round the floor, you're going to round down to the next integer. So all the numbers between 0 and, just below 1, like say 0.9, well, if we're going to round 0.9 down, we round down to 0, giving us all these values at 0. And then as soon as you hit 1 and go past that, say 1.2, well, when you round down 1.2, it rounds down to 1. So all these values between 1 and 1.99999 repeating, those all round down to 1. So that's how we get this little step right here. And then as soon as you hit 2, it jumps up to the next step and then levels off until you get up to 3. So that's how those work. The ceiling function works the same way, except instead of rounding down like you do with the floor function, you round up with the ceiling function. Right? So now you're just rounding up. So at 1.9 2, you would round up to 2. So they're very similar functions. If you have a graphing calculator somewhere in there, there's the ability to graph these floor functions and the ceiling function and just step functions in general.